Welcome to the Explainer. Today, we're tackling something that is literally at the heart of our modern infrastructure, yet it's notoriously abstract. We're talking about reactive power. It's a phenomenon that endlessly frustrates grid operators, confuses engineering students, and creates a true power paradox that utilities spend billions of dollars trying to manage. So we're going to break down exactly what is happening invisibly inside our electrical grids and why mastering this invisible force is the absolute key to modern, efficient power delivery. Let's get into it. If reactive power does zero actual work, why on earth do grid operators care so much? Well, back in the early days of the grid, this wasn't really a huge issue, mostly because generators were super close to the simple things they were powering, like old incandescent light bulbs. But as our grids expanded into these massive interconnected webs, we started adding huge inductive loads. We're talking colossal manufacturing plants and heavy-duty industrial motors. Suddenly, engineers faced a massive efficiency problem that genuinely threatened to overwhelm the entire system. To understand why these industrial additions caused such a headache, we need to quickly define the three different types of power at play here. First up, we have active power. We denote this with the letter P, and it's measured in kilowatts. Now, this is the actual, tangible worker in our electrical systems. When you flip on a stadium floodlight or run a heavy conveyor belt, active power is the energy that genuinely transforms into useful, real-world work. Physical heat, visible light, rotational motion. It's the raw metric that actually gets the job done. In fact, if you look at your home electricity bill, this is primarily what you're paying for. Then we have the troublemaker, reactive power, or Q. This one is measured in kVAR, which stands for kilovolt amperes reactive. Unlike active power, reactive power does absolutely zero direct physical work. It doesn't turn a motor, it doesn't light a bulb, and it definitely doesn't heat up a room. Instead, it just sort of sloshes back and forth, oscillating endlessly between the power source and the load. Its entire job is simply creating and sustaining the magnetic fields that heavy equipment needs to operate. Without it, alternating current machinery just wouldn't turn on. And finally, we have apparent power, or S, measured in kVA. This is the grand total of what is actually being pushed through the physical transmission wires. It's the combination of your useful active power and that sloshing reactive power. But here's the catch. It's a geometric combination, not just simple addition. You can't just add 3 units of active power and 4 units of reactive power to get 7 units of apparent power. Because they operate in different mathematical dimensions, you actually have to use vector math to figure out the total electrical burden your equipment is carrying. So, how do these 3 components interact? Well, it's all perfectly illustrated by the famous power triangle. Think of the real useful power P as the flat bottom base of the triangle, and the reactive power Q rising up on the vertical axis. Your apparent power S is the diagonal hypotenuse connecting them. And the geometry here is absolutely everything. Specifically, the angle created between the base and that hypotenuse. That angle dictates our power factor. The tighter that angle is, the closer our useful power is to our total power. A tight angle means almost everything being pushed through the wires is doing actual work. So, why does this geometry matter in the real world? It's pure economics. Imagine a utility company installs a massive, highly expensive 1,000 kVA transformer to power a growing city. These things cost a fortune. Now, if the system's power factor is sitting at a pretty decent 0.8, that means the grid can successfully extract 800 kilowatts of actual, useful active power from that equipment. But consider the shocking reality of what happens if that power factor drops down to 0.5. Maybe the local industrial sector is flooded with high reactive power from unoptimized motors. Suddenly, that exact same incredibly expensive transformer can only provide 500 kilowatts of useful power. The utility company literally just lost half of their equipment's capacity because reactive power is taking up all the space on the lines. To provide the same amount of real energy, they'd have to build a second, equally expensive substation. It is a staggering financial waste. To help visualize this invisible math, let's look at a classic analogy. Think of apparent power as the total physical effort a horse exerts while pulling a heavy cart down some train tracks. The angle the horse pulls at relative to the tracks is our power factor. If the horse pulls at a tight, narrow angle, say a highly efficient power factor of 0.85, almost all of its kinetic energy translates directly into moving that cart forward. The smaller the angle, the less the horse has to exhaust itself for every foot of progress. But if that horse gets stubborn and tries pulling at a severe 90-degree angle, perfectly perpendicular to the tracks, the power factor drops to 0.
The horse could be sweating, expending maximum effort, pulling with all its might, but that cart isn't moving forward a single inch. In electrical terms, your generators are maxing out the lines, pushing as hard as they can, but all that effort is wasted because it's completely out of alignment with the direction of actual work.
Translating that horse and cart analogy into actual electrical waveforms shows us exactly where this microscopic waste happens. With a purely resistive load, like an old-school light bulb, the electrical voltage and current waves rise and fall together in perfect sync. They are in phase, meaning the power delivered is consistently positive, creating a continuous stream of useful energy. But the moment you introduce a big inductive load, like a factory motor, those beautiful synchronized waves fall entirely out of sync.
Because the current essentially lags behind the voltage by 90 degrees in that inductive load, we run into a fundamental math problem. Total power at any given millisecond is simply voltage multiplied by current. So, when the waveforms are out of sync, you hit periods where one is positive while the other is negative. And as we all know, a positive times a negative yields a negative. This creates frustrating pockets in the cycle where the total power actually dips below zero into negative territory.
And the critical takeaway from those negative dips? Energy isn't being destroyed. It's just being borrowed and returned in a rapid, endless loop. Energy is stored in a magnetic field for a quarter of a cycle, and then dumped right back onto the grid. The grid is essentially being forced to act as an incredibly inefficient battery 60 times a second. If you average that out over a full cycle, the net useful work done by that purely reactive component is exactly zero. Ultimately, the contrast here is pretty wild. While active power is out there doing all the heavy lifting for society, this oscillating reactive power is just acting like a massive bottleneck for the entire infrastructure. It does zero physical work, yet it takes up precious capacity on the transmission lines. And even worse, as it sloshes back and forth across the country, it physically heats up the transmission wires, causing real energy loss, and creates frustrating voltage drops that can literally cause brownouts for the end user. So you are probably wondering, if it causes so many costly problems, takes up so much space, and performs zero actual work, why don't utility companies just ban it entirely? Why not eliminate reactive power from the grid completely? Well, that brings us to a massive paradigm shift about how alternating current physics actually works in the real world. Imagine trying to push a heavy, stubborn wooden cart across a rough gravel road. Active power is the horizontal force pushing it forward. But if the friction from the heavy load on that gravel is too high, the cart simply won't budge, no matter how hard you push. Reactive power acts like a subtle upward force, slightly lifting the cart to reduce that heavy friction so the wheels can finally roll. In an industrial motor, this lift is the creation of its internal magnetic field. Without reactive power constantly priming the system with that necessary magnetic field first, the active power literally couldn't pull the mechanical load forward at all. It's not a flaw, it's an absolute physical necessity. We absolutely cannot live without it, but it deeply congests our lines. So we're left with a vital, high-stakes engineering challenge. How do we balance our modern power grids to provide this essential magnetic lift exactly where a factory needs it, without wasting immense energy pushing that power back and forth across our nationwide transmission lines? It's an incredible puzzle, solved by marvels like static VAR compensators. But we'll leave you to ponder that specific engineering solution for now. Thanks for joining this explainer, and keep questioning how the incredible, invisible systems around you are powered.